This is the screencast for section 1.2, example 10. We're going to learn about horizontal and vertical asymptotes. Now, this notation right here can seem very intimidating, and we are going to learn what that means, but not till later on in chapter 2. I decided that the book kind of brought that in a little too early. We're going to work on that in example 2. You will be not tested yet in knowing what this limit notation means. You will be tested, however, on knowing how to find or where a vertical and horizontal asymptote will occur. We already talked about where vertical asymptotes occur. They happen where the denominator, the x value that makes the denominator equal to 0. So looking more closely at this f of x, my first step is to break this down and factor it so I understand exactly what's going on with the denominator. 4 minus x squared factors into 2 minus x times 2 plus x. So I can see that x equals 2 and x equals negative 2. Those two values are both going to make the denominator equal to 0, but not the numerator. Therefore, I will have infinite discontinuities which are directly associated with vertical asymptotes. So I have a vertical asymptote at both x equals 2 and x equals negative 2 because those two values make the denominator equal to 0, but not the numerator. Horizontal asymptotes are more of a visual process, again, until we get to chapter 2. I can see that a horizontal asymptote is going to occur right here at about, let's see, y equals negative 2. Now horizontal asymptotes, because they're horizontal lines, are y equals negative 2. In other words, the y values are going to approach, get very, very close to negative 2, but not actually touch that. Asymptotes in general are just that. It doesn't matter what happens in the middle of the graph, but towards the extremes of the graphs, way off to the outsides. Asymptotes are an imaginary line where the function will get very, 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 very close to, but never actually touch. So a vertical asymptote at x equals positive 2 and negative 2 means that my x values will never actually touch negative 2 or positive 2. Now, horizontal asymptotes can be touched by the graph, but then somewhere to the outsides of the graphs, way off to the right or way off to the left, that's where they take on the more asymptote form, where the graph will approach that imaginary horizontal line and get infinitely close. Let's look at our examples. Example 10, identifying the asymptotes of this graph. Well, let's see. I think there's a vertical asymptote at negative 1 and positive 2, but my first step is to factor this function so I can see what's going on in the denominator. Let's see. That would be x minus 2 times x plus 1 is how x squared minus x minus 2 factors out. So I can see that x equals 2 and x equals negative 1 are both going to make the denominator 0 only. So we do not have a removable discontinuity. We have infinite discontinuities there, meaning there will also be vertical asymptotes. So we have vertical asymptotes at x equals 2 and x equals negative 1. Now the horizontal asymptote, I think, is going to pass right here visually through y equals 0. Now again, the graph is actually going to pass through the y value 0 right in the middle, but as we go way off to the outsides here, the graph is going to get very, 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 very close to the x-axis, or y equals 0, but never actually touch it. Same thing all the way out here to the left. Now there is, horizontal asymptotes are only a visual process at this point. There isn't a really good way for us to compare a numeric or algebraic answer, so you're going to have to rely on just what you see to determine horizontal asymptotes. The now try problem that goes with example 10 is number 57. Use a method of your choice to find all horizontal and vertical asymptotes of the function. Well, again, finding horizontal asymptotes is going to be very difficult without a graph. I can find vertical asymptotes without seeing the graph, though. I see that the denominator here is going to be made 0 by the x value positive 3. X cannot be positive 3, and the numerator will not be 0 if I plug in 3 for x. That means I have a vertical asymptote at x equals 3. Just to check, I'm going to graph. My numerator needs a set of parentheses, x plus 2. And now my denominator needs its own set of parentheses, 3 minus x. Zoom 6. Now it's kind of hard to see. Okay, first trace, let's check that vertical asymptote. 3. Yep, 3 looks like it has a vertical asymptote there. Plus there is no y value belonging with the x value 3. So I can confirm both algebraically and graphically that I have a vertical asymptote at x equals 3. Now, when looking at the horizontal asymptote, we're going to have to rely on our calculator at this point. We will learn ways to find the horizontal asymptotes exactly, but for right now, it's just going to be an estimate. It's usually going to be some sort of integer. So if I look at the graph here, as I go out to the left, the graph definitely dips below the x-axis, so maybe -1 might be the horizontal asymptote here. But I look over to the right, and it doesn't look like it's quite getting to -1, so maybe I'm going to need to trace out to the right and see what happens, or even adjust the window so I can see farther out to the right. So on my window, I'm going to change my x max to maybe, well, let's go crazy, because if this is an asymptote, I can go as far as I want and it will never go above -1. Well, that's my guess. Yeah, and it does look like -1 is going to be my horizontal asymptote. So no matter how far right I go or how far left I go, I'm never going to go below -1 or here above -1. So I do have a horizontal asymptote at -1. And that would be a y equals -1 because it's a horizontal line. Which means you can also put into y2 as a triple check a -1 and watch that graph so you can see that it does kind of line up. The graph does line up with that horizontal line.